All right, welcome to the video for some practice questions with lessons 11 and 12. Just a couple of questions here to go over. I do apologize for the background noise. It's actually my dishwasher. I'm sitting in my kitchen right now, so hopefully you can get over the fact that there's some background noise here. But let's take a look at some questions here. So the first question talks about the population of kangaroos in Sydney, Australia is decreasing at a continuous rate of 0.0042. So notice that's a rate, not a percentage, so we can change that if we want to, or we can leave it as is, right? It says the population of kangaroos is 140,000 at the beginning of 2016. Approximately how much is left in 2056? So first things first, I notice a big keyword, continuously. So that tells us we're using the PERT formula. So the future value is equal to the initial value, e to the rate 0.0042, so I don't have to change it to a percent, times however many years it is between 2016 and 2056, so 40 years. So the future amount after 40 years is whatever that value is. So we're just using our calculators here for a second. Remember, E you get by hitting second and then the LN button. And we get 165,611 kangaroos. We don't want decimals here because I can't have 0.1 of a kangaroo. That just doesn't make sense. All right, so let's talk again about Newton's law of cooling. So this is the second time I've used this equation. It's come up on the Regents exam in the past, so we just want to kind of be able to use it. All right. So the first paragraph is just re-explaining what Newton's law of cooling is. Let's get to the problem. So it says Detective Sandler of the FBI was called to a murder scene. He arrived at the scene at 2 p.m. and discovered a dead body with a gunshot wound in the main hallway of an apartment building. He measured the ambient temperature of the hallway as 66 degrees. So that's T of A. He also measured the temperature of the dead body, 81.4 degrees. So that is the ending amount. So that's T of T. It says the constant of cooling is 0.0125. And Angela was the only witness, and she estimated the body was killed at 8 a.m. So that same morning, we hear a gunshot at 8 a.m., and he got there at 12 p.m., so that's a total of 6 hours. T equals 6. So we're getting a lot of info here. It says if the average body temperature of a human being is 98.6 degrees, that's the initial temperature, right? Assuming that that was his body temperature when this guy got shot, right? We could figure out if Angela's estimated time of death is correct. So we have all of the variables here. So we're going to plug in everything we know and see if the T of 6 value is the same as 81.4 or close to 81.4, right? I apologize by the morbidness of this question. I've been watching a lot of Criminal Minds on Netflix. So if we go through and type in everything we know, so we want to know, well, what is T of 6? Ambient temperature 66 plus the initial temperature 98.6. That's our body temperature usually, minus the ambient temperature, E to the negative 0.125 times 6. If T of 6 is relatively close to 81.4, we can take Angela's estimated time of death as the real time of death. So all this now becomes is a calculator problem. Can you type it in correctly without making any mistakes? All right, don't forget the E. And we get 81.399. That is super close to 81.4. So we could say Angela's estimated time of death is correct. Number 3, so we have this radioactive iodine. It's treating thyroid disease. It's just a half-life question, right? So its half-life is 8 days. It gives us the function R of X. All right, it even gives us the equation, even better. Then it says to rewrite the equation with X as the only exponent. And then we'll talk about what this all means. So if I rewrite this equation with X as the only exponent, I'm essentially highlighting the rate per day. So if I rewrite this a little bit more, kind of clean up what we have here, right? So the value of the base to the nearest thousandth, so 3 decimal places. So if I do 1/2 to the exponent of 1/8, I get 100 times 0.917. That looks weird. Let me make that look better. To the x. Now, what I really wish I added to this question, and I must have forgot to do it, was to explain what this new base meant. So this new base is 1 minus the rate. Since it's decay, it's minus. So if I do some quick algebra, I can see that the daily decay rate is 8.3%. Right, because I get an R value here of 0.08299, ... So we can see that every day it's going down about 8%. Every 8 days it goes down 50%, so we get that. All right, let's take a look at the last one, number 4. So number 4 talks about the Atlantic sturgeon in the Hudson River. So we have this population S of t can be represented by this function. So we see that this number of its type of fish is growing exponentially over the course of time. It starts at 1250, and it wants us to rewrite this in terms of the monthly growth rate. So we want to make it so that we have an exponent that still has t in it, so still has years in it, but we have the monthly growth rate instead of the yearly growth rate. So to change it to the monthly growth rate, I'm going to change the value inside that parenthesis, the base, 1.42, and raise it to the 1 over 12th power. I'm then going to put on the outside 12t to represent the number of months that we have here, right? So we could just do that. Now I can leave it like that, or I can even rewrite it so that the variable isn't t anymore, where t does not represent years, but make it like something like m for months. But that's not what they asked me to do, so I'll just kind of leave it as is. I could clean this up a little bit. 1.42 to the 1/12th power is some crazy decimal, I'm sure. 1.029, round to nearest thousandth if that's necessary. So if I do that, I actually get 0.030 to the 12t. Now, essentially, since I rounded, I shouldn't get the exact same answer if I plug in the same value for t here and here, but I might get an answer that's really, really close. So it says the value of both equations at 15 years, and round your answer to nearest integer. Let's see how close we actually are, and see how much actually rounding affects an exponential model. All right, because this is kind of like an interesting little experiment we're going to do here. So if we do s of 15 is equal to 1250 times 1.42 to the 15th power. So if I do 1250 times 1.42 to the 15th power, I get 245.67, right, round to nearest integer. If we do s of 15 into this changed model that we have, we should get something relatively close. So if we do 1250 times 1.03, I'm not going to put 3.0 because O is irrelevant, to the exponent of 12 times 15, I get 255,629. Now, you might not think that that's a close number, but in terms of exponential growth, that's actually pretty close. And if you think about it, we rounded this decimal. So with the magic of math, if I put it in with the actual decimal unrounded in my calculator, now this is going to be a little bit of calculator work, so I'm just going to do it for you. Right? So if I do my little bit of calculator work here, I can actually get the same exact answer, but it's because I rounded that they're different. Right? So that's one of the things I wanted to talk about with this problem. Obviously, we want to be able to say when you're rounding something and it's growing exponentially, it's going to change radically over the course of time. It might not change radically over like 2 or 3 years, but if I was to make this go out like 30 years or 40 years, these numbers would be super different from each other. So that means rounding is actually kind of an issue when it comes to exponential models, but just go through and round to whatever the question asks you to round to, and you'll be just fine. Hopefully these questions were good little practice questions for you. Keep looking back at videos, keep studying, right? Your test is coming up really, really quickly, so you can even start working on your study guides and stuff like that as we go through, right? And I'll see you all soon.